Hi boys and girls, this is lecture 2.7 in Unit 2. The topic, the derivative and the tangent line problem. We'll take 2 lectures to discuss this topic, thus this lecture comprises part 1. Calculus grew out of 4 major problems that European mathematicians were working on during the 17th century. The tangent line problem, which we have previously mentioned, and we will be discussing it in more detail today. The velocity and acceleration problem, the minimum and maximum problem, and the area problem. We've also briefly discussed the area problem as well. Each of these problems involves the notion of a limit, which is muy importante, as has been previously discussed. So let's discuss the tangent line problem. We have a curve, and we have chosen a point on the curve. This pink line is tangent to it. We would like to be able to know the slope of this tangent line with information about this point and information about the curve. However, traditionally, we need 2 points to be able to determine the slope of a line. So mathematicians experimented with using secant lines, connecting the target point with a second point on the curve, and then using points that are closer and closer to the target point in order to get secant lines with approximations closer and closer to the slope of the tangent line. But as we said in a prior lecture, as close as these approximations might be, they are still not going to equal the actual slope of the tangent line. Not only is it valuable to know the slope of a single tangent line at a single point on the curve, what we would like to be able to do is know the slope of a tangent line at any point on the curve. Here is an animation which demonstrates this concept. Notice we have a curve, and the moving black dot is illustrating points on the line, and of course the line is tangent at each of these points. When the slope is negative, you can see that the line is red. When the slope is positive, the line is green, and for those brief moments that the slope is 0, the line turns black. You might wonder, why do we care? It's a curve. These are tangent lines. Is this merely an academic exercise? Not at all. When a curve is modeling a real-life situation and representing actual quantities, it becomes very valuable to know what these quantities are doing at a given point in time. When are they increasing? When are they decreasing? When are they static? When will there be a maximum or a minimum? You would want to be able to pinpoint any point on the curve at any point in time and have numeric information about it. Thus, being able to determine the slope of a tangent line at any point on the curve is incredibly valuable information. So let's try to follow in the footsteps of our mathematical forefathers and see if we can use the idea of a secant line approximation to come up with a formula for discovering the slope of a tangent line at a given point on a curve. You can see I have a curve here, and the blue line is a secant line. Let's say that this will be our target point here, and we will label the coordinates of this point x and f of x. Rather than using y, we're going to use the function notation to denote the y value. So this is the point x, and of course on the y-axis we have the function value f of x. Now for our second point on the line, we're not going to say exactly how far away from the first point it is. We're going to say that it is a distance away. It is a change in the original x value, which delta x is notation that we use when we're talking about a change in something, in this case a change in the x value. So since we're moving from x through a change in x to a second point, we're going to let this second point have the x coordinate x plus that change, x plus delta x, which means that the function value at that point on the y-axis will be f of x plus delta x. This means, of course, that the coordinates of this second point are x plus delta x, and then f of x plus delta x, the function value at that point as well. We now have the coordinates of 2 points, and we can use those 2 coordinates to set up a slope formula. So we can say the slope of the secant line is the second y value, f of x plus delta x, minus the first y value, which is f of x, over the second x value, x plus delta x, minus the first x value, which was x. Now you notice in the denominator a little bit of simplification can take place, and the simplified form of this slope formula, f of x plus delta x, minus f of x, over delta x. Now remember that we created this slope function based on the original slope formula. The second y value minus the first y value over the second x value minus the first. Of course, this formula uses 2 distinct points, which is what we created for our slope function as well. But the sleight of hand that we're going to perform here is we're going to let this delta x be very, very small. We need to keep this delta x very, very small because we know that the closer the second point is to the original target point, the better the secant line approximation is to the slope of the actual tangent line. What would be great is if we didn't have to move away from our target point at all, if there were no distance between the target point and the second point. So why don't we let this delta x be so small, in fact let it be no actual distance at all, only a virtual distance away from the target point. We'll use this delta x as a virtual distance away from the original point so that we're able to create a second point, a virtual construct, in order to use 2 sets of coordinates in our slope function. But in reality, this delta x is going to be no distance at all away from the original point, which means we'll be able to calculate a slope using only the information from the one point on the line, and that will give us the actual slope of the tangent line at that point. Does this work, boys and girls? Why, yes it does, to the wonder and amazement of mathematicians all over the world. Now that we have this fancy slope function, let's put it to work in finding the slope of a linear function. You might be thinking, I don't really need that fancy slope function to find the slope of a linear function. It's a line, of course. The slope is constant. And with this particular arrangement of the function, I can see what the slope is. It's in slope-intercept form. That's okay. We're going to use our fancy slope function anyway, just to see how it works. Here it is. The slope is f of x plus delta x minus f of x over delta x. I probably don't have to tell you that this should be memorized. Well, what is f of x in this particular case? We have that. It is 2x minus 3. What is f of x plus delta x? Of course, this means insert this quantity in for x in the original function. So this is going to give me 2 times x plus delta x minus 3. Let's distribute and simplify a little bit. We end up with 2x plus 2 delta x minus 3. Now that we have our players, let's plug them into the formula and calculate the slope. The slope will be f of x plus delta x, which is this quantity, 2x plus 2 delta x minus 3, minus f of x, the original function, which is 2x minus 3, all over delta x. We'll distribute this negative and simplify a bit. We have 2x plus 2 delta x minus 3 minus 2x plus 3 over delta x. Notice that 2x and negative 2x cancel, negative 3 and 3 cancel, leaving us this simplified expression, 2 delta x over delta x. The delta x's cancel, and we find that our slope is 2. Now notice that because the slope is constant in this function, we found that the slope was a constant number. If the slope was variable, there would have been maybe a variable here, 2x or 2x plus 2 or something like that. When we find the slope is variable on a curve, it's not going to come out to be just a single number as it did here because we have a line and a constant slope. In this example, we're going to find the slope of a nonlinear function, and specifically at the points 0, 1, and -1, 2. Notice we didn't have to specify the point in the previous example because, as I mentioned, it was a line. The slope was constant on the entire line. But for this quadratic, the slope is going to change based on the point that you choose. So we're going to create a slope function using our slope formula that we derived, and then we'll use it to find the slope at these 2 points, -1, 2 and 0, 1. Let's start with the function that we created. We have f of x plus delta x minus f of x over delta x. So it's a good idea, I think, to identify what f of x plus delta x is and what f of x is. Of course, f of x is the easier one to identify since that's given. This is x squared plus 1. F of x plus delta x, once again, we need to plug in the quantity x plus delta x in for x in the original function. This means we are going to do a little bit of foiling. And it is a little unwieldy to deal with that delta x term. You may find in some textbooks that they use the letter h here rather than delta x. I've just done this for so many years that this is what I use, but feel free to use h if that's more convenient. So if we're going to FOIL x plus delta x times x plus delta x, let's just do that here, we are going to have x squared, then plus x, delta x is its own variable, then x times delta x again, another x delta x, and then delta x times delta x is actually delta x squared. When we simplify, this gives us x squared plus 2x delta x plus delta x squared. And then remember we had the plus 1. I probably should have written it down each time from the original function. So this is f of x plus delta x. Now we have the major parts of the function. Let's plug them in and calculate the slope. I think this calls for a change in color. The slope will be f of x plus delta x, which is x squared, plus 2x delta x, plus the quantity delta x squared, plus 1, minus the original function. Now be careful because when your original function has more than one term, the negative will need to be distributed. It's not a bad idea to put it in parentheses so that you don't make a careless error. This then will need to be distributed, all over delta x. Might run out of room, but we'll find space somewhere. This is going to be then x squared plus 2x delta x plus the quantity delta x squared plus 1 minus x squared minus 1 all over delta x. Now notice that the terms of the original function will always cancel out in this particular function that we're using, and leaving only terms that have a delta x. So here's where we are now. I'll just continue this up here. We have 2x delta x plus the quantity delta x squared over delta x. If I factor out a delta x in the numerator, this leaves 2x plus delta x over delta x, which means that the delta x's cancel, and here is my slope function for this parabola. I know it's getting kind of crowded here. Remember that we're going to let this distance go to 0. So we're going to let delta x go to 0 here, and that means that our slope function for this parabola is 2x. This will find the slope of a tangent line at any point on this curve. Well, we were asked to find the slope at 2 specific points. So let's find the slope at -1, 2. We'll only need the x coordinate. That's going to be 2 times -1, which of course is -2. Therefore, the slope of the line tangent to the point -1, 2 on this curve is -2. What is the slope at 0, 1? We probably have guessed what it is already, but using the slope function, 2 times 0, we get, of course, that the slope is 0. Now realize that what we have found here is a way to find the slope at any point on this curve. And again, that is an amazing accomplishment. We have now laid the groundwork for discussing the derivative of a function. It turns out that this slope function we derived is the basis for the limit definition of a derivative. What we add here is taking a limit of this function as delta x approaches 0. The f prime of x here refers to the fact that a function f of x, once you take the derivative, is f prime of x. That is notation indicating that we're looking at the derivative of a function. This is also known as the difference quotient. The process of finding a derivative is called differentiation, and differentiation is one of the two fundamental operations of calculus. The other is called integration. Notations denoting the derivative include f prime of x, which we saw previously, y prime. You might also see dy dx. Sometimes you might read that the derivative of y with respect to x, but more commonly just dy dx. And here are a couple of other notations denoting the derivative. You don't see these as often as you see the other three, but those are the notations that you will be using. Let's find the derivative by using the limit process. The function f of x equals x cubed plus 2x. Notice I have stated here the limit definition of the derivative, which perhaps you already have memorized, who knows? But of course eventually you will do so. As I've stated before, it's a great idea to write down what f of x and f of x plus delta x are. We already have f of x, so let's write down f of x plus delta x, just to see what we're going to be inserting into the limit definition of the derivative. This means, of course, that x plus delta x would be inserted in for x in the original function. This is going to give us x plus delta x quantity cubed plus 2 times x plus delta x. Now, this means we would have to FOIL x plus delta x 3 times, but in order to save us a little bit of time on the video, I have already done that work here. Feel free to take a look, inspect my work, and verify my conclusions at your leisure. But for now, we're just going to go back to the limit definition of the derivative and use the conclusion I have there. We're going to be taking the limit as delta x approaches 0. Remember, eventually we want this distance to be 0. Of f of x plus delta x, which is going to be x plus delta x quantity cubed, that is x cubed, plus 3x squared delta x, plus 3x delta x quantity squared, plus delta x quantity cubed. And then remember, that's just x plus delta x quantity cubed. We also need plus 2 times x plus delta x, so I'll distribute that here. Plus 2x plus 2 delta x. Now that we've written down f of x plus delta x, we have to subtract f of x, the original function, minus x cubed plus 2x, and all of this over x squared. Delta x. Now let's rewrite this, distributing the negative here. We still haven't taken the limit yet. We're not actually able to at this point because plugging 0 in for delta x gives us a denominator problem. What we're hoping will happen is as we continue to work with this quotient, the delta x will cancel, and then at that point we'll be able to use direct substitution to take this limit, but we're not ready yet. So we have x cubed plus 3x squared delta x plus 3x quantity delta x squared plus delta x quantity cubed plus 2x plus 2 delta x minus x cubed minus 2x, all over delta x. Now, as I stated before, the original terms of the function should cancel here. The x cubed, the negative x cubed, the positive 2x, the negative 2x. Notice the only terms we have left contain a delta x. So let's rewrite our limit and factor out that delta x. We'll have a delta x. That's going to leave 3x squared and then plus 3x with a remaining delta x. We'll have 2 left after taking out the 1, so this will be delta x quantity squared, and then plus 2 all over delta x, and now we have arrived at that moment where we can cancel out the delta x in the denominator, which means now that this has been reconfigured, we'll be able to use direct substitution to take this limit, placing 0 in for all of the remaining terms that have a delta x. This is 3x squared plus 3x delta x plus delta x quantities squared plus 2. And taking this limit means that all of the terms with delta x become a 0, leaving 3x squared plus 2, the derivative of our original function x cubed plus 2x. In our last example, we're going to use the derivative to find the slope at a point on this function, f of x equals the square root of x. We will look at the points 1, 1, 4, 2, and 0, 0. Here is our limit definition of the derivative, so let's get started. F of x, of course, is the square root of x. F of x plus delta x, inserting x plus delta x into the original function gives us this, the square root of x plus delta x. Our limit will look like this. The limit as delta x approaches 0 of f of x plus delta x, which is the square root of x plus delta x, minus the original function, which is the square root of x, over delta x. Since we have to take a limit here, we'll use any method which allows us to reconfigure this so we'll be able to use direct substitution. This looks like a prime candidate for our rationalization technique. So let's multiply top and bottom of this fraction by the conjugate of the numerator, which will be the square root of x plus delta x plus the square root of x. We have to multiply the numerator and denominator by this quantity. In the numerator, we're multiplying a binomial times a binomial, so we will need to FOIL. We'll have the limit as delta x approaches 0 of the square root of x plus delta x times the square root of x plus delta x is simply x plus delta x. The square root of x plus delta x times the square root of x is the square root of x, the square root of x plus delta x. This is a bit of an awkward term, but we're going to leave it like that because what's going to happen next is we get the negative of this exact same term. And for our final multiplication, the negative square root of x times the positive square root of x gives us negative x. In the denominator, remember, don't distribute. We want to keep that delta x separate because we're hoping it cancels at some point. So we're going to have delta x times the quantity x plus square root of x plus delta x plus the square root of x. When we simplify the numerator, the x's cancel, these awkward terms cancel, and we're left with just delta x in the numerator. So this is now going to be delta x over delta x times the quantity, the square root of x plus delta x, plus the square root of x. The delta x's cancel, which gives us now the limit as delta x approaches 0 of 1 over the quantity x plus delta x, square root of x plus delta x rather, plus the square root of x. We are now able to use direct substitution and let this delta x go to 0. Then we'll have this simplified expression, 1 over the square root of x plus the square root of x. Since those are like terms, we can write this as 1 over 2 square root of x. And this is your derivative. Of course, it will also tell you the slope at any point on the curve. So now let's take a look at this graph. We want to know what the slope of the tangent lines are at the points 1, 1 and 4, 2. we're going to use our slope function to get those numeric values. So the slope at 1, 1 is going to be 1 over 2 times the square root of 1. You only need the x value in this particular function. 1 over 2 times 1 is 1/2. So the slope of the tangent line at the point 1, 1 is 1/2. What is the slope at 4, 2? We would have 1 over 2 times the square root of 4. That is 1 over 2 times 2, which is 1/4. So at the point 4, 2, the slope of the tangent line there is 1/4. As you know, this function will find the slope of the tangent line at any point on this curve. But what is happening at the point 0, 0? Let's try to use the function we found to find the slope at 0, 0. But notice, of course, we're going to have an undefined value, something that should never happen, 0 in the denominator. This means that the derivative does not exist here at the point 0, 0. Furthermore, there's a vertical tangent line at the point 0, 0 in this graph. That's it for today's rather lengthy lecture. And I leave you with this final piece of advice. You might want to check your tan lines. God bless you, boys and girls.